In this second application lecture, we will look at current and current density and look at the connections with circuits to our previous work. Well, before doing this application study, what is the application? Why are we doing this analysis? Well, what we're going to find out is that by looking at the first principles we've been discussing involving electric fields and potentials, we find out that they can be used to analyze circuits and obtain some of the circuit equation principles that you learned in 251 and 253. We actually know one of these already, but have not emphasized it. What is the circuit analysis principle that comes from the equation below? The integral along a closed contour of E dot dl is equal to 0. To further understand the circuit analogies, we're going to repeat the table we looked at when we studied Gauss's law, and we're going to look at current flow. And notice that in current flow we have a new vector variable J, which is equal to rho v. Now J is called the current density, and it's actually a flux density as well. It has units of amps per meter squared. It's a product of charge density rho times the velocity of movement of the charge carriers. Now, in total analogy with the water flow and electric flow, we're going to define a little bit of flux as a little bit of current equal to the dot product of J with a little surface element. So this is something we already know. We have a flux density J just like the flux density D, and find its projection through the vector-oriented surface element ds to get the little bit of flux, in this case the current. So the total flux is obtained by integrating over an entire closed surface, or maybe not an entire closed surface depending on the application. But if we're looking at a source situation, that's what we'd be seeing. Look at the sources. In the case of electric flow, it's coulombs, but in the case of current flow, it's coulombs per second. And coulombs per second we know is amps. So the source density, we'll find out, in fact, is coulombs per second per meter cubed, or coulombs per meter cubed per second. And that will give us an idea of what the source is going to be like for the situation of current flow. Now let's look at a picture. To understand better, let's look at our famous little cube, and we'll look at some current density flowing in, Jn, and current density flowing out, J out. It's a flux density. In this case, I'll say that J out is equal to J in, and in that case, the net flux through this cube is equal to 0. Now, if we look at this expression, J dot ds equals 0, and use the divergence theorem that we learned in Math 264, this surface integral becomes this volume integral, and it's equal to 0. Therefore, the integrand is equal to 0, and the divergence of J is equal to 0. This volume here is the actual volume of our cube, and there are no sources of current in that volume. So the equation del dot J is equal to 0 is what equation that we learned in basic circuit analysis in EECE 251 and EECE 253. Now let's repeat the previous picture where we now pass through this cube here, and J in and J out are different. So J out in this case is greater than J in. So now the net flux is going to be non-zero because we've accumulated some source effects from inside this cube to give us a greater value of J out. So there are sources inside the cube. Now we do exactly the same as we did before. We do the surface integral over the closed cube, and equate it to the volume integral of the divergence using the divergence theorem that you learned in Math 264, and we find that in fact that this del dot J must equal to some source effect. So we want to look at this source effect. What are the sources of the increased value of J out? J out as we travel through that cube. So we picked up something. So what have we picked up? What's contributed to the increase of J out? All right, this is a repeat of the previous slide where we identified del dot J is equal to sources here, and we have the sources as we go from the cube into the cube. Flux density J in, the incoming current density, the outpouring of current density is increased. So there are sources that helped us get that increase of J out inside that cube. And we also know that J is equal to rho V. By dimensional analysis, we have to have some idea that the source is going to be have these dimensions: coulombs per second per meters cubed, or coulomb per meter cubed per second. So coulomb per meter cubed is charge density per second, and it's instantaneous. So we might think that there's some time derivative involved of charge density. That's intuition directly from looking at the units. Let's continue with the analysis. Well, in this slide, there's really nothing new. It's a repeat of the previous slide. Del dot J is equal to sources. We have some idea of the dimensional analysis of what those sources should look like. But in order to really appreciate what's going on with the sources, I have to do a demonstration in class. Come to class to see the answer to the source question in a student-led demonstration. In the previous slide, after looking at the demonstration that you will see, we will know what the sources are. So now we really have a complete description of the current density. Let's look at what we have and see how we can relate it to circuits. Well, we have that J is equal to rho V, where V is the velocity of charge carriers. In a metallic conductor, this velocity is called the drift velocity and is proportional to the electric field. That proportionality constant called mu is the mobility. For electrons, because they are negative charge carriers, we'll have a minus sign here. So here we see this is the rho for the rho V, and the V is this piece here, the mobility times the electric field. For positive charges, we write it in this form. This quantity rho times mu we call the conductivity. So if we substitute sigma into rho mu, we get J is equal to sigma E. This again is another famous circuit equation that you use in analyzing your circuits in EECE 251 and EECE 253. One last point I'd like to make in our discussion of the current density J are the boundary conditions for J. I think you can guess what that might be. We did this for D. D was epsilon E. Now we have J equals sigma E. By looking at the figure, can we guess what the boundary conditions for J should be when we cross an interface? From the previous video, we had that for D, the electric flux density, that the normal components were continuous across the interface, and D is equal to epsilon E. I don't think it's a big stretch to guess what the boundary conditions should be for J, since J equals sigma E. Well, the physics for J are identical for the physics for D insofar as the boundary conditions are concerned, because we're looking at flux across interfaces. And in exactly the same way we did for D, we can do for J. And as this is summarized in this slide, we're not repeating all the algebra that we did in the video when we looked at the boundary conditions for D, the electric flux density. For the current density, the conditions are the same. The normal components of J must be continuous across the boundary. In summary, in this application, we have established the usefulness of the current density J as a new flux density variable. We have obtained the three basic equations of circuit analysis, and we've also obtained the boundary conditions for J across an interface and saw that it was equal in essence to the boundary conditions for D, the electric flux density across the interface.